Can you connect these three homes to water, gas, and electricity without the lines crossing? Well, let's try. We can connect the blue house to electricity, water, and gas easily enough. And then the greenhouse, we can connect it to electricity, we can connect it to water, and we can connect it to gas, again, without problem. And then what about the red house? Well, we can just about connect it to electricity if we squeeze through here. We can certainly connect it to the gas, but now we've blocked off the house from water and we can't connect it in any way. And in fact, any way you try to draw the lines, it's not possible to solve this problem. Now, why might that be? And is there a fix? Well, let's talk a bit about graphs. This is a graph, and by graphs, I don't mean pie charts and bar charts. We have points known as vertices, and we have edges, which are lines which connect them. And I only care, for example, there is an edge between vertex 1 and vertex 2. How I draw the line doesn't matter. So, for example, if I rub this line out and connect like this instead, that's actually the same graph. Now, graphs can either be planar or non-planar graphs. A planar graph is where we can draw the edges such that none of the edges cross. Now, you might think, well, these edges cross. And you'd be right. But the thing is, we can replace this edge connecting vertex 1 and vertex 4 with a new edge which goes around the outside. I've still connected the vertices in the same way, but now none of the edges cross. And so therefore, because we can draw the graph without the edges crossing, we call it a planar graph. However, with this graph here with 5 vertices, there's no way of redrawing the edges in such a way that they don't cross. So this is a non-planar graph. Now, a complete graph is one where every vertex is connected to every other vertex. And we use the letter K to indicate a complete graph. So K3, for example, means we have 3 vertices and we connect every vertex to each other. So this top one is connected to these bottom 2, and this one on the right is connected to the other 2, and the one on the bottom left is connected to the other 2. So we can connect every vertex to every other vertex without the lines crossing, and therefore this is a planar graph. Now, K4 is when we have 4 vertices. Can I connect every vertex to every other vertex? Well, yes, I can. The top left, I can connect to the other 3. The top right, I can connect to the other 3. The bottom right, I can connect to the other 3. And the bottom left, I've already connected to the other 3. So K4 is planar as well. Now, K5 is not planar because there's no way to connect every vertex to all the other 4 vertices without the lines crossing. So if I start the top one, I'm going to draw 1, 2, 3, 4 edges. And then the vertex on the left, I can connect that to the 4 other edges. So 1, 2, 3, 4. But then I start to get stuck as I try to connect each of the other vertices to the other ones without the lines crossing. So K5 is not planar. And now we're getting closer to the original problem. We've got something called bipartite graphs. And that's basically where we have a number of vertices at the top and a number of vertices at the bottom. So K1, 2, for example, means we have 1 vertex at the top and 2 vertices at the bottom. And we want to connect each of the red vertices to all the green vertices and vice versa. Now, this one is easily possible because I can just add 2 edges like this, and now all the reds are connected to all the greens. What about K2, 2? Well, it's possible again. I need to connect this top left red to each of the greens, and I need to connect the top right red to each of the greens. So this one here, and as long as I draw a line like this, it's connected to the other green. So that's fine. And what about K3, 2? Well, we can still do it. The left red, I can connect to the 2 greens easily. The middle red, I can connect to the 2 greens easily. And then the right red, I can still connect to the 2 greens easily like that. But when we get to K3, 3, it's not possible to draw a planar graph where the edges don't cross. And you can see that this graph here, where we're connecting each of the reds to each of the greens, is equivalent to our original problem where we're connecting houses to utilities. Now, here's a quick informal proof of why we can't do it. There's something called Euler's formula, which connects the number of vertices, edges, and faces, or regions, in the graph. And basically, if we take the number of vertices, subtract the number of edges, and add the number of faces, for a planar graph, we should always get 2. So, for example, this graph here, which is K4, the complete graph for 4 vertices, the number of vertices is 4. You can see we have 1, 2, 3, 4 vertices. The number of edges is 6. We've got 1, 2, 3, 4, 5, 6 edges. And the number of faces, which we can think of as regions here, we've got 1, 2, 3, and then a fourth region which is outside of the graph. And you can see if we do V minus E plus F, we do indeed get 2. Now for K33, we can see that we have 6 vertices. We have 9 edges because each of the 3 top dots is connected to each of the 3 bottom dots. That's 3 times 3. And if you were to use Euler's formula, if the graph was planar, then the number of faces, the number of regions, would have to be 5 to obey the formula. And the reason this is impossible is because it's easy to show that each region in this graph would have to be surrounded by at least 2 edges. So therefore, if we had 5 faces, there would have to be at least 10 edges. However, there's only 9 edges, and therefore we don't have enough edges, and therefore it's impossible for Euler's formula to be obeyed, and therefore the graph cannot be planar. However, there is a fix if we use non-Euclidean geometry. This is a torus, which you could think of as a donut. And if you were to put the houses and the utilities on the surface of this torus, this donut, then it is possible to connect all the houses to all the utilities without the lines crossing. And I'll leave that as an exercise for you.